Hello, everyone. Welcome to Reinventing Access Control for Fingerprinting Credential Protection. So today I'm going to show you why traditional credential-based security are fundamentally broken. And we can fix it, something that you already do, leak it out of your browsers, your devices, your networks, that is your digital fingerprint. So before we begin, something about myself. So myself, Aditya Singh. I'm an independent security researcher. I work as a cybersecurity analyst at a startup called Turtleneck. I have been a research collaborator at IIT Bombay. I've worked as a threat analyst intern at NCIPC. My few papers have been accepted at BlackHat, Middle East and Africa, Nullcon, and other BSides events. Now, this is our table of contents for the next 30 minutes. So we'll start off with the introduction, then we'll move on with browser and device fingerprinting, then move on with network and hardware, and then its implementation, and then comes to the pitfalls. Now, what exactly is fingerprint, right? So fingerprint refers to collecting unique characteristics of your devices, your hardware, your browser, and creating a digital fingerprint that is unique to you and your devices and your network. Just like your physical fingerprints are unique to you, these physical fingerprints are unique to you. These digital fingerprints are unique to you and your devices as well. And that's what we are going to use and showcasing these different techniques that we uses and different websites use to track you and analyze you. But how different is the fingerprint? Is different from the cookies that have been coming on from the years, and you know that these are used for this tracking from the websites. So cookies can be deleted by the user. These can be manipulated. It requires your user's consent to that you consent to be tracked by the cookies. They don't work in incognito mode. They can be easily deleted or manipulated. But that is a different case in fingerprint. You don't need the physical consent from the user. This is more of a passive collection. It doesn't require any user interaction. It works in incognito mode. It combines hardware, software, and network characteristics. And it is much harder to spoof or manipulate. So cookies are more of like a name tag that you can remove from your browser, and when you visit the website again, it'll think of you as a new user. But that is not the case with the fingerprints. It'll more like a DNA. It'll stick to you, and it is much harder to change. We have mainly 4 types of fingerprints that we will be discussing. The first is the browser. That is the fundamental of device intelligence. That's where the unique identification of website visitors starts from. Then the second is the device. Gathers hardware characteristics and uses them to give a device identification fingerprint. Then comes the network part. We uses network characteristics, communications to fingerprint the devices. Then comes the side channel. So that uses hardware processes, and using the things that it leaks out while processing stuff is where we use the side channel fingerprint. And each of these layers adds entropy, making the combined fingerprint more incredibly unique to you. So let's dive deep. The first one is browser fingerprinting. These are the list of fingerprinting characteristics that we use or the company uses to track you. The most common are the browser name, the browser window sizes, the list of installed plugins, what extensions do you have, what fonts do you use, the canvas, the WebGL, audio fingerprinting, and some unique ones are favicons, but the list goes on. We are going to talk about the first one is the audio fingerprinting. So audio fingerprinting is a browser identification technique that uses web audio API. So this is a really common API that is being used in the browser and websites commonly. This works by how your particular browser processes the web audio API, how your OS combines with it, and makes it unique to you and your browser. Now this works in incognito modes as well, so it doesn't just works in the normal browsers. This has 4 main components. The first one is the offline audio context, the oscillator node, the dynamic compressor node, and the audio buffer. We'll start off with a demo. So this is a demo of the audio fingerprint. So let's say that so we are generating a test tone using the offline audio context. So now this doesn't necessarily plays sounds in your speakers, but rather uses mathematical function to generate an oscillator wave using sine and wave functions. And then we used a dynamic compressor node. So what it basically does is, so it so it highlights the differences that is used by your browsers. So these inconsistencies are mainly used to fingerprint you. Then we just process those inconsistencies, and then we compute the mean fingerprint. That is, in this case, is 124.0.434. Now this differs when we use it in a different browsers, because how different browsers actually uses it. So this is the Firefox browser. Now, this is the same exact code that is being opened in the Firefox. Now, we are again using the offline audio context. We are applying the dynamic compressor node. We are just capturing the buffer. And then, but the value is different in this case. That is 35.7499. That is because how Firefox and Chrome are different in cases of how they actually processes those web audio APIs. Now, this will work in incognito mode as well. So if we open just the website again, the value should be different if it was in the case of cookies, but the values would still be the same because we are using a browser API, not just the cookies. So the value is still the same, that is 124.0.434. Now, each browsers generate a different due to math optimizations. So they initially started out with the same Google WebKit that was developed by Google back in 2011, but due to different variations, how they actually started processing them. So Chrome uses Blink plus Web Audio API, so it uses hardware acceleration. Firefox handles the floating operation points differently than the others. Safari has a different process of rendering the samples. The Brave has a different approach. So Brave uses a method called farbling. So what it basically does is for each web audio API that is being called, it gives a single value to each calls. So it kind of creates a plane for each of the values that it gives. Then in the Tor browser, it is not possible for us to use web audio API because it is completely disabled in that case. And that is but because this works in incognito mode in most of the cases, that is what it makes it powerful to use it. Then next up is the canvas fingerprinting. So canvas fingerprinting is using your HTML5 canvas elements to create a unique identifier. We create different canvases, the text shapes, and uses sub-pixel anti-aliasing behavior, how they actually render on your screen, how they actually render on your browser, and uses these characteristics to identify you. Now now this is the canvas fingerprint. So now let's say that we are creating a 2D rendering output. We are just creating different images, and then we are rendering different text fonts into this browser. And using this, we extract a pixel data. And then with pixel data, we generate a hash either by using, you can just use SH256 or whatever. And then using these hashes, you get a particular fingerprint that is unique for this browser. And if that is different for the other person. Now, this values differs based on what kind of graphics drivers do you have, what OS do you have, what fonts do you have installed, if you have different extensions. So these value changes depending on that. Next up is a much more unique and pretty interesting is the favicons. So favicons is short for favorite icon. It also known as shortcut icons, website icons. This is a file that associated with a website. So these websites, these favicons are mainly used to identify which websites they are. Now, to prevent downloading favicons every time we visit a website, they are stored in a favicon cache by the browser. Now I have a video playing the exact favicon demo. So now let's say that we visit a website called localhost/identity, and then it initializes the fingerprint generation stream. Now what this is doing is it is processing those data stream that is coming from your browser. After identification, it gives you a unique identification value. So in this case, this is 93AD, and that. So let's call it number 35. So now this should be unique to you, but let's try again. Maybe it creates a different value. Now it again processes those same data streams, and the value is still same. Now you can say that this might be because we have the same browser session open, so the website might have still saved those data. So we reopen the browser, we revisit the same website, and then the website again initializes its own fingerprint scanner and just do the same process again, and then the value is still the same. Now you can say that this has been saved in the site data and the cookies and values. So we clear the site data in the website to see if it creates a different fingerprint value now. Now we start the scan again. Then it again processes the same data streams, and the value is still the same. But maybe the developer options were broken, so we will now try to clear the cookies out of that website. So we are now just clearing out the cookies and the site data that we have stored for the last hour. Then we try it again. Then it again processes those same data stream and then gives you the value. And it's still the same. It's still the same unique identifier that we had when we visited the first when we visited the website for the first time. Now, how exactly does it do it? So there are two main parts: the writing the favicons and reading the favicons. So for example, for the writing the favicons, so let's say that the user first visits, let's say target.com. The victim visits the website. It gets to the main index page. The server returns the index page. Then it goes on to the next /a on the same website. Now, the server returns the a.html. Then the user's browser requests the favicon icon of the website A. Then the server returns the favicon icon of the website A. Then goes on to B. Then the b.html gets returned again. Then the user asks for favicon icon for B. But this time, the server doesn't return a favicon icon for B, and it just denies the request. Then comes it for the C. It returns it follows the same process. It first gets the C, it gets the C.html, then it gets the C favicon icon, and then the server returns the favicon icon for C. Then we get the target for D, and then it again denies the request for actually getting the favicon icon for D. Now this is the writing of the favicon process in the user's browser. Then comes the reading the favicon part. So once you have visited the website and now you again revisit the website, how will the actually server read and who you actually are? So there comes the reading the favicon part. So again the user visits the index.html, it gets the index.html, then it gets to A, and then it gets to a.html. Now because this already has, the browser have stored the favicon of the a.html, it doesn't ask for the favicon icon of A. Then it returns to B, then it gets the B.html, but this time because it doesn't have a favicon icon stored for B, it asks for the favicon icon for B. But rather than returning a favicon icon for B from the server side, it gets an error 404 because the favicon was never there. Then follows the same process for C because the C has the favicon icon for C in the user's browser. We get the C in the C.html. Then comes the D.html has the favicon, doesn't have a favicon icon stored, it asks for it, it gets denied the request. And using these, we create a bit. So for A and the C, we have a favicon icon stored, and for the B and the D, we doesn't have a favicon icon stored. So using this, we create a bit ID of the user and who he actually is. Now, when the browser, using this exactly state of delivered and undelivered state, we create a unique pattern for this. Now, this was initially working for Brave and Firefox as well, but then they fixed it after the version 1.14. Now, the Brave has fixed it, so it can't be used for there. But in the Chrome, it's still accessible. It is still doable. In the Safari, it is still doable for the Mac OS and the Android. We haven't tested on Windows system. The Edge is still working. The Firefox version works on Windows and Mac OS. It was initially used to work on every system as well. And that is how we can be tracked by the favicon cache as well. Next comes the device fingerprinting. So we have these characteristics for the device side as well. We have the OS version, the CPU type and architecture, the GPU type, what RAM size, storage capacity, battery, sensors, camera, and the list goes on. We will be focusing on the main three parts: the CPU, the GPU type, and the math functions. Starting off with the GPU fingerprinting. So GPU, graphical processing unit, is a technique that is tries to identify your graphics card based on which exactly is it. So it queries it uses the WebGL API of the browser. That is a really common API that is being used in the browsers. It then queries the GPU render string. It gets the vendor information, whether it's NVIDIA, AMD, Intel, etc. It tests the rendering capabilities and performance characteristics of that graphics card. And then it renders the precision behavior. So how exactly precise is the graphics card is. Now this is, yes. So now this is the WebGL system architecture. So initially it is using the WebGL API, it is querying the browser to give its GPU or graphics card information. Then we get these information out of those GPU card. What version it is using, what vendor it is, what vendor unmasked it is, what render unmasked, what exactly the version of that graphics card is, what shading language version, and then using these values, we create a fingerprint. Now this can vary depending on each devices. This can be same for some cases, because if we have this two devices for the same system, right? So let's say that if you have two same macOS, this WebGL parameters would be same, but there comes the different part, that is the WebGL extensions. So WebGL extensions is something that is a part of WebGL, and you can use supported extensions. So this gives us a list of extensions that is supported by that WebGL API, and then using this, we can create different fingerprints. So now, what shader precision does it have? What kind of attribute does it support? What it doesn't support? And using this, then we create another fingerprint for this using just with WebGL. Now, each extension has its own parameters. So using these, we include texture formats, the rendering of limits, what a vendor-specific features does it comes with, and using this, then we create the fingerprint for using the GPU. Then comes the math fingerprinting. So math fingerprinting basically uses how your browser and your devices actually uses or processes mathematical functions. So it uses floating point precision variations. So different processors, operating systems, what your browsers are, will create a different slight variations in how they actually process those mathematical functions. Those variations can be in rounding behavior, in precision handling, in edge cases results, in subnormal number handling. Now here we are running a mathematical precision engine. So we are running different kind of mathematical operations in the browser. We are just running different mathematical functions. Then using these functions, we immediately get a result. And these results differ from browser to browser and from devices to devices based on what kind of variances that they have. And using these different values and the results that we get, we create a fingerprint for this mathematical fingerprint. Now these values can differ based on what operating systems do you have, what architecture do you have. It can be either x86 or ARM. What browser do you use? What JavaScript engine? So if you have a V8, like my system have a V8 with JavaScript engine, if you have a Spider Monkey, it will be different than that. Then what kind of hardware do you use? And these are the variants. These are the few characteristics that varies your fingerprint from devices to devices. Then comes the network fingerprinting part. So we have mainly three parts: the TLS fingerprinting, the packet interarrival times, the TCMP and ICMP header timestamps. We will be talking about the TLS fingerprinting. So we all know what a TLS handshake is. It's an initial communication between the server and the client when it initially starts the encrypted communications. Now each server communication and the client's communication starts with a TLS handshake. Now using these handshakes, we extract those informations out of those packets before the encrypted communications actually starts. So now this is a JA4 fingerprint that is commonly comes with the Suricata and Suricata. This comes with Suricata inbuilt. Now using this JA4 fingerprint, so let's say that server and client starts its communications. So they are using what protocols that they are using, what TLS versions that they are using, what SNIs do we have, what cipher suites they have, and what kind of extensions, then the truncated SHA-256 of the cipher suites, and the cipher suites of the truncated head SHA 256 of those extensions, and the signature algorithm in which they have appeared. And using these, we create a TLS fingerprint. Now, this doesn't necessarily comes with the usage of tracking. This can be also identification of anomaly. So let's say that if you have an all Linux infrastructure and suddenly you see a pop-up of a Windows J4 fingerprint that is different from what your servers have been normally generating. So now this is something that you can look into to see if what kind of an anomaly this is. Now, this can be used to identify the C2 malware communications as well, because for their servers, these fingerprint is calculated before the encrypted communications actually happens. Moving on, we have the side channel fingerprint. So these are the few lists: the CPU, the clock deviations, the quartz crystal variation, the anticipate drift, the CPU timestamp counter, and the sweep counter attacks. Now, we will be only focusing on two, that is the CPU and then the clock deviations. The CPU fingerprint is a browser-based fingerprint that extracts your CPU's hardware characteristics. So it uses mainly its 6 distinct benchmarks. That is the targeting data cache size, the cache the cache associativity, the TLB capacity, what page size does it have, what core counter, the single core performance. And using just these 6 benchmarks, it creates a fingerprint that is unique to you, even if you have the same kind of CPU for 2 devices. So these techniques fundamentally uses 3 main APIs, standard APIs that comes with the browser, that is Performance Now, the shader array buffer, the web workers, and with WebAssembly. Now, what exactly sophisticated in these are that they can extract microarchitectural details that is tolerated when they are manufacturing those CPUs. Now, for example, the cache size fingerprint. So they create a random chains of memory called pointer chasing. The CPU loads this memory from its fast internal storage called the cache. When the memory chain gets bigger that they initially started to, the cache will exhaust, and then the CPU will load a little slower. And by measuring these showdown, this script can use to know what kind of CPU L1, L2, and L3 cache sizes are, and this differs you from the other CPUs. Then comes the TLB, that is translation look-aside buffer test. So your computer keeps a fast shortcut list of TLB that it tries to fetch the information out of it. These script accesses those memory exactly 1 page at a time. So for it just accesses those enough memory to avoid the trigger of TLB. But if it takes longer than the initial steps, then you can know that how much space of that TLB of that CPU is. Then comes the clock deviation. So time-based device fingerprinting leverages the fact that every computer has its own internal clock, and each clock uses quartz crystal oscillator. Now, these quartz crystal oscillators has an internal clock, and now no two crystals can oscillate at the same frequency. These differences that is introduced in those 2 quartz crystals creates the clock skew that can serve as a unique signature as well. Now, we compare these tiny differences into those functions, and we get independence fingerprint for that clock. And then we compare it with another clock that is independent from that system, and then we get a value of those discrepancies, and then we use it to create a fingerprint. Now, each device has its own unique timing characteristics due to what kind of manufacturing tolerances that they have, what crystal oscillator that they have used, what temperature variations that they have, the power management, the behaviors, the hardware aging, etc. Now, this is more concerning because this is unavoidable. Unlike the other fingerprints method that you can just simply disable disabling them useless by disable the web APIs and the JavaScript. This doesn't exactly use your browser's APIs. It uses what CPU do you have, and it optimizes. It uses those performance monitoring. So websites normally use this performance monitoring metrics to see how exactly your browsers are performing, and they can disguise these clock skew deviations to showcasing as that they are just monitoring your browser's performances. Now, how exactly do we integrate these into your access controls, right? In traditional access control systems, we always have been using these login passwords, the MFA and everything. But why don't we use something that we are already leaking out of our own devices? We can combine these different characteristics to make a fingerprint that is unique to each devices. Then we can combine these multiple layers of browser devices, the network, and have a unique identity to them. Now, we can also use it to verify them alongside while they are logging into their system or into their organizations or into their websites. Now, this doesn't necessarily bother any user because this is running in the backend and the user doesn't have to add an extra step in the verifications. It enhances the security against phishings, and using these, we can have a more of an extra layer in the defense. Now, this working primarily in 3 stages. That is the initial fingerprint while they are authenticating. So while they are logging into their website or into their systems, we can initially use it to parallelly run the fingerprint characteristics and then verify them, even if their credentials are correct, whether their fingerprint matches or not. Then comes the continuous session verification that we can continuously try to verify those systems. So even if they have the correct fingerprint when they're initially logged in, whether they still do have those same fingerprints when they logged in. Then comes the anomaly detection and threat response. Now this can come handy in these threat responses as well. So for example, if a browser comes with the same credentials that they have a correct credentials, but their fingerprints differs from what they initially registered. So this can be put into an anomaly category. They can either be blocked, or they can be put into a DMZ, or they can be put into something of a more secured network side. Now there are some pitfalls as well. These can be mitigated with new browsers, with more privacy-focused browsers. For example, the Brave is the most privacy-focused browser as of now, and it has a method called farbling. So it reduces those fingerprinting techniques by injecting random outputs. So for example, if value of the web audio API was 124 for the same browser, if we refresh it, then it will give a value of 120 because it randomizes those outputs that they initially gave it from the browser. Now, these farbling methods have been known to bypassed by using the fuzzy matching fingerprints, despite these minor differences, and they still have been known to bypass. I mean, initially the Favicon cache fingerprint was completely ignoring the Brave farbling methods, right? Now, this can be used to obviously identify those spam attacks, your account takeovers. So even if you have the right credentials, you won't be able to log in if it gets phished. Now comes the common questions. So isn't fingerprinting like a privacy violation? So it is not, because these are commonly used by websites and other softwares to monitor you and track you. But so this is not exactly a privacy violation because you don't need to give a consent to be fingerprinted. And aren't companies like Google already using this? So they do use it. So they use it more of a risk-based authentication. So they don't necessarily block the user out of the system if they have a wrong fingerprint, but they use it more of a risk-based. So if a user has a change in its fingerprint, but how variations have it brought into the fingerprint, and using this, it will be brought into a risk-based. I mean, how much risk does this user holds? So if the user has a completely changed fingerprint, it has a different geolocation IP, it has a different screen size and everything. So this will be much on a higher risk than on someone who has logged in from a different browser rather than using their same browser. Can this be bypassed by spoofing or automation? So not exactly, because for bypassing all of the unique characteristics, you have to have a lot of materials on the expenditure. You need to have exactly that same GPU, the same CPU, with the same browser that they have, the same extensions that they have, the same fonts that they have installed and everything. And doesn't browser updates changes in these changes the fingerprints? So it does. It does in the case of browser fingerprint, but it doesn't in the case of the CPU fingerprints, in the device's fingerprints, in the network-based fingerprint at all. So yeah, that's all I have. Thank you.